very much. I want to thank the organizers for a terrific conference and say, indeed, it is an honor and pleasure for me to be here to celebrate my former students' conference. So what I want to say is I want to talk a little bit about Sasakian geometry. That's not the theme of the conference, but hopefully we can connect things up. So let me start with a brief history, I guess. I don't know if I should be up here or down there. All right. So in the late 1970s, when I was working here in Mexico, I started working on some graded differential geometry, supermanifolds in particular. Adolfo became my student at UNAM, not quite sure what year, but he, and in 1981, Adolfo began his doctoral studies at Harvard, ultimately under the direction of Shlomo Sternberg. And Shlomo in that time was very interested in kind of graded differential geometry. By the mid-1980s, I had changed my direction of research to the study of Yang-Mills moduli spaces, self-dual 4 manifolds at that time. But then in the late 80s, Adolfo and I began a project to describe super Yang-Mills theory. Never quite, well, this resulted in only one publication about the action of Lie supergroups on supermanifolds. So Adolfo, of course, continued to develop supergeometry while I returned to the study of Yang-Mills moduli type problems and then to under the study of Sasakian geometry, which provides a large class of Einstein manifolds, namely they're called Sasaki-Einstein manifolds. So my motivation was to find examples, or at least prove the existence of Einstein metrics on certain compact manifolds. And there was, if you look back in the book of Bess on Einstein manifolds, it was not known at that time if there are a whole lot, if there are few, any of that. We now know that there are too many, basically. But anyway, Sasaki-Einstein manifolds. So here's a problem, right? That I felt, well, this is good for this conference. Let's unite supergeometry with Sasakian geometry. That sounds, well, maybe kind of crazy in a sense. I don't know. In anytime you have a differential manifold, you can put a structure of a supermanifold on it in many different ways. But I think there's actually a canonical way of doing things with Sasaki-Einstein manifolds. In other words, there's a canonical, I think, this is not something we have so far, but a canonical way to associate a supergroup action on first of all, a supermanifold structure on a Sasaki-Einstein manifold, and then with a supergroup action. And this is through what are called killing spinors. So these are the kind of keys to the unification of Sasaki-Einstein geometry with supermanifolds. What? Oh, wrong button. All right. So let's talk. People probably don't know too much about Sasakian manifolds here. One can think of them kind of morally. You want to think of them as kind of an odd dimensional version of Kähler structures. If you know what a Kähler geometry is, this is kind of the analog in odd dimensions. So we're going to work with a closed manifold, that is a manifold without boundary, dimension 2n plus 1. And it'll be a contact. We'll have a contact structure. So we have a contact form which satisfies this condition everywhere on the manifold. And this defines what's called a contact structure. So a contact structure is actually an equivalence class of these one forms that satisfy this equation. but that differ by a nowhere vanishing function. But let's take it to be positive to select what's called a co-orientation. So we have a subbundle, D, of the tangent bundle, which is the kernel of eta. And of course, it doesn't matter which one of these etas you pick, you still have the same D. So that's an implicit, or that's that's what defines the contact structure. And you can think of it as having a conformal symplectic structure because you can change, and we'll get to that in a moment, I guess. But anyway, so the pair is called the contact manifold. So the manifold, the smooth differential manifold with this codimension 1 bundle is called the contact manifold. So now if we choose a 1 form, so that gives us that's more structure. And in fact, one can show that this is very well known, one can show that there's a unique vector field associated to that choice of 1 form. It's called the Reb vector field. And it's dual in this sense that eta on C is 1, and C, interior product with the exterior derivative of eta, vanishes. Along with this comes a foliation of the manifold called the characteristic foliation. So one-dimensional foliation. And they come in basically 2 types. One was called quasi-regular. And the quasi-regular means that each leaf passes through any neighborhood at most k times. If k is 1, then it's regular. And this regular would correspond to a circle bundle over a base manifold. In that case, the manifold will be the quotient space. In this case, quasi-regular case, I should say more. It generates a circle action. So you have a circle action on there, and if k is equal to 1, you'll get a principal circle bundle over some smooth. It'll be Kähler manifold. I'll have more to say to that in a minute. And otherwise, it's called irregular, and certainly most contact forms will be irregular. Yeah, well, there it is. Now there's more more structure here. We can compute on this codimension 1 vector bundle, which has even dimension. We can choose an almost complex structure. There are many compatible almost complex structures, and so we choose to satisfy these 2 conditions, right? And so we can also extend this almost complex structure, which is defined on the codimension 1 bundle D. We can extend that to the full tangent bundle by simply saying that it annihilates. It just kills the Reb vector field. Okay, so once you have all that set up, there's a compatible metric, kind of a canonical compatible metric that one can construct. Namely, you take d eta, and you compose it with that endomorphism tensor 1 plus eta tensor eta. And so this gives you a Kähler structure in the transverse direction to that Reb foliation, right? So it has a transverse Kähler structure, but that depends on the choice of a 1 form. So if you're doing contact geometry, you can think of it as a conformal symplectic structure because you're going to be multiplying it by a conformal factor. Anyway, this quadruple is called a contact metric structure. So the 1 form together with its Reb vector field, the endomorphism, and G, the Riemannian metric. Okay, so I've already kind of indicated that. You have a transverse symplectic structure, transverse Kähler structure when eta is fixed. So we will be interested in the condition where so this has an underlying CR, almost CR structure. We're going to be interested in the case when it's an actual CR structure. So one can write down a Nierenhuis tensor there, and the vanishing of that tensor gives you the existence of a CR structure in this case. This CR structure has some nice properties. Its Levy form is non-degenerate, and it's what's called strictly pseudo-convex CR structure. Yeah, and that's what I just said, that we're mainly interested in the integrable case. Okay, so here's the definition. We finally get to the definition of Sasakian. So this contact metric structure is called K-contact if that red vector field is a killing vector field. Right? It's just a killing vector field, which is equivalent to saying that it leaves that endomorphism invariant. And it's Sasakian if this CR structure is integrable. And in which case then the transverse metric is Kähler, right? And you have transverse holonomy UN. So and this is what's called, this contact structure is called a Sasaki type. So this is the thing that we're interested in, this quadruple when it's Sasaki, and when all this is formed, you have a contact structure, strictly pseudo-convex contact structure, a fixed CR structure with it, and then the red vector field is a killing field, and the CR structure is actually a CR structure, an integrable structure. So one can look at this in terms of, and it turns out that this, although I'm not going to be talking about it, this idea of looking at the metric cone has enabled us and others to move more forcefully in the right direction, mainly with respect to geometric invariant theory, and something I might mention a little later on. But this cone turns out to be an affine variety, and that's the reason. So it's a lot easier to work. Here I'm just saying, okay, it's Kähler. If our structure down here is contact, then this thing will have a natural symplectic structure. Forget about the metric, you can get a natural symplectic structure. But if it's Sasakian, this thing will be Kähler. It's if and only if. And I'd have to tell you, so we're not going to use that too much, so I could give you more of the details, but I decided not to, I guess. Some properties of the Sasakian manifold of dimension 2n plus 1. Okay, so what are they? Well, any Sasakian structure has at least an S1 symmetry because of that killing vector field, right? Well, you might ask, that could just be a line, but if the orbits of the red vector field is a line and not a circle, then you're going to get another circle that's nearby, and that'll come up shortly. So the characteristic foliation is actually a Riemannian foliation. So that's related to the fact it's actually Kählerian, that the transverse holonomy group is actually UN. If S is irregular, then the closure of the foliation is actually a torus of dimension between 1 and n plus 1. So that's what I was saying before. If you have, so the irregular Sasakian structures, that is, if you have a Sasakian structure, you have irregular red vector field. It has some nice properties compared to any arbitrary red vector field because it's like an irrational flow on a torus. And so it can be approximated. So there's a nice approximation theorem due to Ruckenbühler which shows that. So the metric G is bundle-like, and the leaves of the foliation are totally geodesic. So bundle-like means that all of the, if you know anything about Riemannian submersions, then all of the O'Neill formulas in that work for bundle-like metrics. This is a term due to, I think, Bruce Reinhardt. In the quasi-regular case, an S1 orbifold. So if you look at the quasi-regular case, we're on a compact manifold. It turns out that there's always a quotient, and it's a projective algebraic variety, but it has an orbifold structure. right? So the orbifold structure is very important there. So, and you have to think of the orbifold as a different category, right? So the Ricci curvature satisfies this condition here with respect to when the Reb vector field is here. So this tells you immediately if you're going to have an Einstein metric, if that metric, which is a Sasakian metric, is also Einstein, it's going to have a positive Einstein constant, right? So it's always positive, and that means that this projective algebraic variety. That means that this projective algebraic variety is Fano. So the anti-canonical line bundle, or it's an Orbi bundle, is ample. Okay. So on a compact Sasakian manifold, we have the group of automorphisms, and I mentioned, so that group always has a maximal torus, right? So it's and that torus has some dimension between 1 and n plus 1. So the n plus 1 is the contact analog of toric geometry. So if you that's the maximal torus, and in that case, the cone, that Taylor cone that's over that, will be a toric cone, a toric affine variety. So there's another cone which we call the Sasaki cone. Some people call it the Reb cone. I like to call, well, we defined it first, so I'm going to call it the Sasaki cone. So the Sasaki cone is the following. You take the Lie algebra of that maximal torus, and you think of them as vector fields on the manifold, because that's what they are. They're all isometries of the manifold, and then you look at the ones that are positive. You have a chosen Sasakian structure, so there's a fixed eta, there's a fixed one form, and then you look at all of the Reb vector fields, all of the Lie elements in the Lie algebra of the torus that satisfies this positivity condition, and such that this thing is Sasakian. Well, that will be guaranteed to be Sasakian. So I just put this up here for emphasis. This is what we call the unreduced cone, because you can divide by the Weil group of whatever group of automorphisms you have a group which leaves the CR structure invariant, and that's a compact Lie group, and so that has, of course, a unique maximal torus up to conjugacy, but you have the action of the Weil group of that. Okay. So the Sasaki, so that's what I'm saying here. So that's the reduced one, that's the full one, but we almost always work with the unreduced guy. And you should think about this as the moduli space of Sasakian structures whose underlying CR structure is DJ. Okay, so while I mentioned this is the toric case, so now there's an affine cone, which I'll say a little bit more about. We're not really going to use it very much, but and here's what I'm saying about some of the geometry of it. So one can extend that almost complex, or that complex structure on D. You can extend it to the tangent space of this affine cone in this way. You take this Liouville vector field R by dr, and you say that psi is minus I times C. This defines C, so you have this. You kind of have a cylinder of these things, right, over the Sasakian. All right, so Mg is Sasakian if, well, I mentioned that before, if and only if Cm is Kähler. Now, Mg is Sasaki-Einstein if and only if that cone is a Ricci flat Kähler. Okay, so that ties into kind of Calabi-Yau metrics, that special case of that. So these last two statements can be used. This can actually be used to define Sasaki and Sasaki-Einstein. The reason the reason that I say that is I'm going to introduce some definitions that I don't want to go technically very far into the details of it, and that is, what is a 3 Sasakian manifold? So if this affine cone up there actually, with all this gadgetry, has a hyperscalar structure, if you know what that is, so you have basically 3 orthogonal Kähler structures hanging around, right? And this ties into the quaternions. Then the Sasakian manifold is actually 3 Sasakian. It actually has 3 orthogonal, well, I have them written here. So 3 orthogonal Sasakian structures with Reb vector fields as, let's say, 1, 2, 3. The metric satisfies this, and they satisfy the Lie algebra of SU2. So you have an SU2 there, so you actually have a 2 spheres worth of the Sasakian structures there, right, as you move around. So that's called 3 Sasakian. We studied this before we started studying the Sasaki-Einstein. And the reason we did that will come up in a moment or so. But of course, I'm just mentioning here, corresponding to these vector fields, these Reb vector fields, there are 3 contact 1 forms. So this is also what can be called a quaternionic contact structure. So it's that analog. Yeah, okay. So the Sasakian is Sasaki-Einstein if the metric is Einstein. That is, it satisfies this condition. I'm going to say a bit about Sasaki-Einstein because that's what's going on. Here's the reason that 3 Sasakian manifolds are automatically Einstein. This was a result of Kashiwada back in 1970s. So Sasakian geometry was first studied by Sasaki, although he didn't call it Sasakian geometry, but that's where it first came from. And he wrote down a lot of the fundamental things, fundamental details about that. And Kashiwada came along with this 3 Sasakian. Well, this was defined by Kuhl and others, but Kashiwada came along and saw, just doing a computation, that these things are automatically Einstein. That's the way we got into them. We said, hey, there's a lot of Einstein. But back then, they didn't think there were many of these things. A sphere in dimension 3 mod 4 has a 3 Sasakian structure automatically. Okay? A sphere in any odd dimension has a Sasaki-Einstein. The standard round sphere is Sasaki-Einstein. The standard round sphere in dimension 3 mod 4 has a Sasaki-Einstein, a 3 Sasakian structure. Okay, so these things fiber over quaternionic Kähler orbitals. Now, in the regular case where you have a manifold, that was a result of Ishihara and Konishi, and then myself and Chris Galitsky and Ben Mann showed this for the quasi-regular case where it's over orbitals. There are no irregular 3 Sasakian manifolds, by the way. Many 3 Sasakian. So we got many examples over orbitals. The only examples that were known before were basically spheres. There's also a classification of the homogeneous spaces that are 3 Sasakian, and it turns out that there's one for every compact simple Lie group. So SE metrics on S1 orbitals. So we got into then trying to study the case where we get Sasaki-Einstein, not just 3 Sasakian. And so we did this, Chris Galitsky and I started this in 2000 or so, and we produced a whole lot of examples, right? And I'm just going to mention some of these examples. So they even live on exotic spheres. Now, what you do here, just let me say something quickly about, if I can. So you take d eta and you deform it. So this is deforming the contact structure with an isotopy. But I mean, all contact structures that are isotopic, they're equivalent. So you're not but you deform it like this, del bar of some function phi, right? And then you write down, so you write out a metric. You have some Sasakian structure, which is positive, and I didn't say exactly what that meant, but if you think about it over an orbifold, let's do that, then the anti-canonical Orbi bundle is ample. So this then gives you just like Yao's proof of the Calabi conjecture, you do the same thing. You use the continuity method, and so you look for when do you get an Einstein metric, right? And so you have to satisfy a Monge-Ampere equation, right? And there are obstructions. So, what? Yeah. This is another, yeah. Oh, another marker. I thought you wanted another metric. Okay, maybe turn the light, or maybe can everybody see this? Not. Anyway, d eta. Geez, with my writing, it's going to turn out to be worse. Okay. So anyway, you get a satisfying Monge-Ampere equation on that, and there are obstructions. There's an obstruction which I'm not going to go into, which is quite interesting. And the problem, of course, this terrific problem was just solved by Chan, Donaldson, and Son for Kähler manifolds, getting necessary and sufficient condition on the existence of Kähler-Einstein metric, relating it to geometric invariant theory stability. That problem is open in Sasakian geometry. There are some interesting known results, but it's still an open. That's called the Donaldson, Tien, Yao, and conjecture. But anyway, so there are tons. There are just infinitely many Sasaki-Einstein metrics on a bunch of manifolds, and in particular, they exist on exotic spheres. At least we have them up to 15. Because we put them on a computer. This uses Brieskorn manifolds. It's not the standard ones that Brieskorn use. That obstruction applies to them, so they don't work. They don't give you Einstein metrics. So but the point here of all of this is there's a whole lot of Einstein metrics, right? And so I'm just mentioning some people's work on this. So the upshot, basically, I guess the upshot of all of this is that there are more Einstein metrics than you want. There are so many. I think, I mean, we have, for example, here's one that I always felt special about, the 13-dimensional sphere. That does not have any exotic differential structures, which are bounded by parallelizable manifold, right? So there's one diffeomorphism type there, and that has something like a finite number we got, but 10 to the 9th, somewhere around there, Sasaki-Einstein metrics, and the moduli space has dimensions somewhere around 2 times 10 to the 13th. Right? So there are these horrendous numbers of these things, and just recently, Collins and Silkilhidi proved that S5 has an infinite number of Sasaki and Einstein metrics. We only had a finite number on S5. I don't know if I put that in here. That's a very recent result. And I just mentioned this Donaldson, Tien, Yao conjecture. So Einstein, Sasaki-Einstein, that's where we got to right here. Okay, so let's kind of shift gears a little bit. I want to talk about killing spinors. What's a killing spinor? Well, okay, so you have a spin manifold. So the first thing you need is a spin manifold, right? So the Clifford, this definition of Clifford bundle is just the tensor bundle modulo this ideal, okay? So a real spinor bundle is a bundle of modules over over this Clifford algebra that forms an algebra. And of course, there is a topological obstruction. By the way, I didn't mention any Sasakian manifold because it has that, because the structure that it has, let's just say, is automatically oriented. When you choose that complex structure and so forth, you end up choosing an orientation. So any Sasakian manifold is oriented. But then any Sasakian manifold is not necessarily a spin manifold. But it turns out that let me, before I get to that, just state it. Any Sasaki-Einstein, any simply connected Sasaki-Einstein manifold is spin manifold. Okay? Has a spin structure. All right, so of course spin structure might not be unique. I guess it is if it's simply connected, but in general it might. So anyway, here's a definition of a killing spinor. So a killing spinor is a section of that spin bundle that satisfies this equation, this quite simple equation, where this is given by Clifford multiplication. Right, and then alpha, this number is a complex number. Okay, this alpha, and it's either real or it's pure imaginary. If it's pure imaginary, then it turns out, this is a result of Thomas Friedrich, that the manifold has to be non-compact. So that's not the case that we're interested in. We're in fact interested in the other case. This is a quite remarkable theorem of Friedrich that says that if you have a Riemannian spin manifold which admits a non-trivial killing spinor, then it has to be Einstein. And it's Einstein with scalar curvature equal to this, and you see why that scalar curvature will be negative when alpha is a pure imaginary number. For us, in our case, we want alpha to be real, in which case this is always positive, which is the case we want, right? Okay, so a killing spinor is actually an eigenvector of the Dirac operator. So the Dirac operator is found here where you take a local orthonormal basis and you define this operator. Nabla, of course, is just the Lebesgue-Civita connection, and it has eigenvalue minus n times alpha. A killing spinor, which is not identically zero, has no zeros, another property of it. And here's another interesting thing, and that is that a killing spinor naturally gives you a killing vector by just kind of composing in this way with the metric. Okay, so we always have a killing vector in a Sasakian structure, right? So we're happy about that. So a Riemannian spin manifold is of type PQ if it carries, this definition, P linearly independent real killing spinors with alpha greater than 0, and exactly Q linearly independent real killing spinors with alpha less than 0. Every simply connected, here's what brought me to talk of, right? Every simply connected Sasakian manifold admits non-trivial killing spinors. Sasaki-Einstein, not Sasakian. So Sasaki-Einstein always admits non-trivial killing spinors. That's a result of Friedrich and Koth. So back in the 80s or 90s, late 80s, something like that. It's known for a while, but it hasn't really been used. So killing spinors, why do I want to take Sasaki-Einstein geometry and unite it with supermanifolds? Because of these killing spinors. Because if you read physicists, killing spinors give rise to supersymmetry. Right? So that's the reason. That's where we're heading. And here's another kind of remarkable thing. In arbitrary dimension, the only things that have killing spinor, the only manifolds that have killing spinors are either spheres, which have a lot of them, or Sasaki-Einstein. That's it, in arbitrary dimension. Now there are two more dimensions. There's one with which is related to the octonions with the G2 holonomy. Okay, so there are a couple more, but they're not in arbitrary dimension. They're only in actually 6 and 7, dimension 6 and dimension 7. So we have these types. So if the dimension of Sasaki-Einstein manifold is 1 mod 4, then the type is this 1, 1. So you have two killing spinors, but they have a different type. They have that number, that killing number is different. So they don't form a vector space, for example. Whereas in 3 mod 4, they form a vector space. They can because they have the same killing number. So 3 Sasakian manifolds have more killing vectors. So they have m plus 2, where the dimension is 4m plus 1. Okay, so that I've said. And here's the only other case admit real spinors are the round spheres. Of course, those are, other than Sasaki-Einstein, because the even dimensional spheres, of course, can't be Sasaki-Einstein, but they admit killing spinors, right? The odd dimensional spheres are Sasaki-Einstein. And in manifolds in dimension 6 and 7, whose Riemannian cone has holonomy G2 or spin 7, respectively. So that's everything, all compact manifolds, compact, that admit killing spinors. Okay, so now we're getting to supersymmetry and supermanifolds. So, so what's a supermanifold? Well, here we've talked about it. We've had several, many talks, I guess, about this. So I'll just be very brief. So we have this RMN, where we just have Rn. We have Rn endowed with a structure sheaf that looks like C infinity functions on Rn. Well, let's say with determinants theta 1 up through theta m, and these are going to be the odd vectors. So you're looking at that, the ring generated by that over the C infinity functions on the even part Rn, right? So this generates an exterior algebra, and A1 you can think of that generated that nilpotent ideal. So C infinity, yes. So that's a supermanifold M is a space which has an underlying structure there, just the space of manifold, which will be a manifold that is locally isomorphic to this guy, to this, with structure sheaf this, right? This AM, which is this on M. Okay, so you're going to glue things that look like this. That's a supermanifold. Morphisms, of course, preserve the Z2 grading. Note that this guy is an ordinary manifold whose structure sheaf is just the quotient there. Since theta I are nilpotent, well, you might want to think of these better in terms of schemes, although they're not commutative. They're Z2 commutative. They're graded commutative, right? But because of these nilpotent elements, it's convenient to think of it in terms of scheme. Now, Lee's supergroup is a group in the category of supermanifolds. So now, what is supersymmetry? Well, that's a harder one. Because it comes from the physicists, and they don't define things really. I mean, they work with them, and they get a lot of good results, and they have amazing ideas, but they often don't define things. Although in this case, they probably have. But I'm being only because I grew up in physics. I'm being harsh on the physicists, but. Supersymmetry was defined as a symmetry in quantum field theory between fermionic fields that anti-commute and bosonic fields that commute. So in quantum field theory, you have these fields, and you have, for fermionic case, you have to use the kind of what they call anti-commutator instead of a minus sign in the commutator, right? In mathematical terms, one can work with bundles of Clifford superalgebra modules. The generators of supersymmetry should form a Lie superalgebra. I've read a bunch of stuff in the physics, but I have a hard time finding this kind of thing. They usually just say, oh, here's supersymmetry, and then they write down the Majorana equation or whatever, and start computing. So here's a simple example of a Lie superalgebra that people that work with them certainly know this example very well, where you have just two one-dimensional algebras here. G0 is generated by, say, d by dt. T is an ordinary variable. And G1 is generated by this guy, q d theta plus theta dt. They satisfy the Z2 graded bracket relations, which are this, right? And they're Z2 grade. I didn't go into, people know, I think, what Z2 grading is. So this generates the action of a Lie supergroup on this R11 space, namely, it's this. So I tried to understand. So the next thing I tried to do was, okay, let's try to understand what are the physicists doing? What is this supersymmetry? But Dan Fried got there. He has a nice little set of lectures, 5 lectures, I think, on supersymmetry. And so he's explaining that to mathematicians, right? And so this is what I found very accessible. So we have a baby example that's in Dan's lectures. So you have a Riemannian manifold, and let's say you have a map which represents a classical, let's say it's a classical particle, the movement of a particle in time. So R is time, right? This manifold can be Euclidean space. It can be a representation of a spin group, which is the one we're interested in, or more generally, some Riemannian structures related to these so-called nonlinear sigma models that physicists use. They can be Kähler and hyperkähler things. Okay, so then you also have this fermionic superparticle, phi, that is an odd tangent vector. This is what Dan Fried says. It's an odd tangent vector along the path. So that's his interpretation of this fermionic superpartner. This can be described then by a map, R11 to N, such that the pulling back, so I is the natural inclusion here. I don't know, did I write it down somewhere? Yeah, right here. So it's the inclusion of R into R11. So you pull back phi by I, and you get this X up here. And then this fermionic superpartner is pulling back not phi, but d phi, where d is this odd derivation. So you pull that back, and you get phi. Okay. And this inclusion map is defined here, the obvious kind of thing. Now, this has what's called, physicists work with a Lagrangian density. So this has this Lagrangian density here. And this is invariant under this group. Now, although it might not be completely obvious at all, and I didn't go through the computation, it's just playing around with maps a little bit. So L is invariant, this Lagrangian density is invariant under the Lie supergroup G generated by these two guys. Notice that D has the minus sign here, Q has this. So what is this? This is a supergroup R11 with the right and left actions. Right? One of them is a right action, the other one is a left action, right? Whoops. Yeah, I guess that's, do I want to, yeah, is there anything more? No, okay, so I'm there. So the talk is really about a bunch of questions. We started talking with Adolfo and Mitch Rothstein, and maybe we can even have some answers at some stage. Help from Joe. So I want to understand the following implications. Well, some of them we can understand, right? First, Sasaki-Einstein gives you killing spinors, gives you supermanifold with supersymmetry. Well, this part, of course, the first part is clear, right? Now we know we've seen this, so we're over here, right? And this is the folklore. According to physicists, killing spinors give rise to supersymmetry. So exactly how does this occur? Is there a general recipe that associates a Lie superalgebra to a vector space of killing spinors? I mean, so what we want, right, what I think we should have is you have these killing spinors. You have Sasaki-Einstein. You have killing spinors there, and somehow there should be canonically associated, maybe one, maybe two, maybe the, but some associated superstructure with a supergroup action that encodes that supersymmetry, that tells you what that supersymmetry is doing, right? That's kind of the idea. That's the hope, right? Given a Sasaki and Einstein manifold, can we associate a supermanifold structure such that the killing spinors, in some sense, generate, whatever that means, a Lie supergroup action on MA? So that's the question that I think we want to answer. And that's the end of my talk. And muchas felicidades, Adolfo.
I do.
Yeah.
The association of supersymmetry was by just the physicists of St. Luther's just wrote down a basis for the Graded Algebras basis for the differential. And which one also makes a difference. But then they became the same thing.
Yeah, no, that's kind of the idea that we're thinking about, exactly that, right? You're right. These kind of generators that we have here, we have to write down the right superalgebra, and we'd like to do it in each of the cases, right? So we have three Sasaki, and we have this case where you don't have a vector space, you have two, but not a vector space. So there, I would assume that, maybe there's one associated with one of these guys, one superstructure, and another superstructure with the other. And so there's not a uniqueness there. But in the other case, in dimension 3 mod 4, one's a vector space, so it's not clear exactly how you get the red vector field out. When you have two, we have to see, right?
I noticed that you sort of shy in putting, once you have a killing spinor, which is not identically zero, then it has no zeros.
Yeah.
Then it is a global section of, it defines a global section.
Yeah.
So if you have like two linearly independent spinors, like in one of the cases that you show n plus 2, I guess was the other one, then you have is it true that you have a trivial subbundle?
Well, you probably do, I would think, right? Even like in the 3 Sasaki, in case you have n plus 2, so you should have, if they're linearly independent, you get somewhat.
At any rate, if you have that, then you can use that subbundle.
We can use it.
If we have that, we can use that as the bachelor bundle of to define a supermanifold structure. I believe that in Juan's talk, he mentioned this structure of derivations that when you take this structure to the structure sheet of a given supermanifold, then you sort of split all the supervector fields into vector fields in the manifold with coefficients in the structure sheet, and something that comes from algebraic derivations based on the vector bundle.
Yeah.
And as a matter of fact, some of the representations that immediately was using Mitch in producing the Graded Algebra representation were just like that, were just these kind of derivations. So I think that one of the answers is that yes, we can do it. I mean, and you're sitting in it because once you have killing spin or even one killing spinor, you already have a whole bundle on top of this manifold and use it with the structure of the derivations that Juan showed us in his talk.
Yeah.
That's
Yeah. No, it should, I agree. It should be very possible. Yeah. Yeah.
I wrote a lot.
What?
I wrote a lot. Okay.
You wrote a lot, okay, good.
My question is, if all these correspondences between Sasaki-Einstein, physics, supersymmetry, etc., can be translated to the Lorentzian case?
To Lorentz.
The Lorentz manifolds.
Lorentz.
A metric with a...
Yeah. Any Sasakian manifold has a Lorentz structure. It's good because you have this one direction of the red vector field, so you can change. You change to a Lorentzian metric. Because there's an obstruction to having a Lorentzian metric, and that is you need to have a one-dimensional foliation, and that's what we have.
Do you know if there are similar results in that case?
Yeah, I mean, I'm sure that things will work there, although I haven't been working with that structure much, so in the Lorentzian case. But of course, that's going to be closer to the physicist's part, for obvious reasons.